Good morning, everybody. Thank you for being here today. So today I will present you Helicoid technology and a few applications we have been working on lately, mainly related to automotive and how to enable sustainable composite in high-performance applications. So first of all, let me start from the really origin of the technology. And what we tried to address was one of the key weaknesses of fiber-reinforced composites, specifically their poor impact performance. And this is a problem that affects a wide range of applications, from wind rotor blades, hydrogen pressure vessels, automotive components, area structures, down to sporting goods application. The main reason is we tend to use in conventional FRPs brittle reinforcement and sometimes resin systems that leads to damage localization, poor energy absorption, and therefore poor impact resistance and structural integrity. And as a result, we tend to overbuild structures to meet safety and performance requirements. What we did is to get inspired by nature. And in fact, in nature, you can find several architectures that have developed to resist impact and to protect animals and plants from external threats. And specifically, we looked at the mantis shrimp. This is a very aggressive animal. It uses its club to strike prey it feeds on, like an hammer, and it manages to crack shells, which are considered to be quite tough themselves. If you look inside the microstructure, you will see that is composed by UD layers, very similar to a conventional laminate design that we use today in engineering, which are slightly rotated one to respect to each other to form this helicoidal distribution of fibers. So compared to a traditional layup where we tend to use large interply angles, larger than 30 degrees usually, in helicoid we smooth the change in fiber orientation with angles lower than 30 degrees. And we also use blocks of traditional layup to tailor stiffness and strength of the laminate. The benefit of these are, first of all, we reduce interlaminar stresses. Therefore, we allow to delay the lamination onset in the composite. But more importantly, when damage initiates, you get this type of failure in the structure, where you can see a cross-section of the actual club, and in white you see a lot of matrix failure. So the energy gets dissipated through matrix cracks, diffused through matrix failure, and you leave fibers undamaged. You create these highly complex fracture patterns in your structure that allows you to dissipate energy, but at the same time to preserve a very high structural integrity. Unique selling points of the technology, as I said, is a 2D fiber architecture. So you can use with any type of fiber, resin combination, and material formats, as long as you can maintain an alignment. So continuous fibers in a UD, multi-axial NCF, or aligned short fiber composites. Is tailorable to be fully quasi-isotropic and make therefore full rotations with the helicoid architecture, or directional to have a preferential loading direction in your structure. We support the implementation through dedicated software and failure codes that allows to simulate performance of our helicoid layups. There is no capital investment for the deployment because, again, you can use the same manufacturing process and technique that you have been using for processing UD or multi-axial NCF. Is IP protected, which gives you a competitive advantage when you license the technology from us. There is a strong branding opportunity as well that's more relevant for applications where we work, for instance, in sporting goods. And as I will show you later on during the presentation, we enable also sustainability in high-performance application by enhancing performance of bio-based materials as well as recycled composite. And the technology works as in cross-market applications. We have applications in sporting goods, automotive, aerospace, defense, and so forth. Let me give you an example of our solution in one of our key development that we have at the moment is related to automotive EV battery enclosures, and it's in collaboration with TPI Composites and Sartex. And I'm not going to spend too much time on this because I'm pretty sure you are aware of the importance of this application in the composite industries these days. So we are looking at deploying the technology in the protection cover of the battery pack of an EV vehicle. So the part that needs to resist impact from the road. So beyond all the requirements that the part has in terms of fire resistance, MEI shielding, and so on, one key requirements for mechanical performance are resistance to perforation as well as reduce deflection, because also during an impact you don't want the battery pack to crash against the battery protection to crash against the battery pack. It's also a high volume production solution, more than 3,000 tons per year per vehicle, high rate manufacturing, and for this specific application we use multi-axial NCF with a thermoset solution and a liquid composite molding. So this is just to explain you how we add value to the supply chain. So for this application, there is a supply chain already in place. We've got a weaver, Sartex, that supplies fabric to TPI, that molds the part and sell it to the OEM. So Helicoid interacts with the entire supply chain, tier 2 and tier 1. We work with Sartex to engineer the fabric. We work with TPI to engineer the design of the part, because eventually what we deploy is a new, more efficient layup sequence of the part. And therefore, the idea is that we want to add value to the supply chain to enable more business for the entire supply chain, because in this way, Sartex is able to sell more of their materials with Helicoid technology to TPI, and TPI has a competitive advantage against other tier 1 for a more efficient structurally solution. Let me go then to the development itself. This is how we usually interact with companies in general. So we start off with a design phase. In this case, we received a reference solution from TPI that was making use of a combination of biaxial NCF and woven layers positioned on top and bottom of the protection cover. The woven layers are there just to protect from impact, and they add cost, more expensive than a multi-axial NCF. The idea was to remove the woven layer and deliver a solution with our Helicoid design, fully multi-axial NCF, with improved damage performance and reduced deflection. So we performed, with our set of tools, a 3D FEA model. We have a set of advanced 3D failure criterion that are capable of predicting the performance of the Helicoid structure. Not going to spend too much time on the results, but the idea is that we can down select the optimal Helicoid layup sequence in such a way that we delay the occurrence of fiber failure. We promote the formation of this subcritical matrix damage that I showed you earlier, and we reduce interlaminar stresses so that we delay the onset of the lamination damage. The next step was then to work together with Sartex to engineer the fabric and make sure that we can deploy the stacking sequence into a multi-axial NCF design. We build the plates, infuse them, and then perform the impact test based on OEM requirements, in this case 350 joules of impact on the plate. We performed impact using an instrumented drop weight tower and a custom-made test rig, again based on OEM's requirements. And this is the type of results that you get. So you can get a full force displacement of the load history during the impact. This is for the commercial reference, doesn't say much by itself. But if you overlay the Helicoid design, here we were targeting same weight, just improved performance. You can see how our design was capable of achieving a 25% increase in load-bearing capability of the underbody protection, and more importantly, a 20% decrease in deflection. Again, we are using same fiber, same resin, just an optimized architecture. This is not the old story. In fact, if you look closer to the point of maximum load in the structures, you can see that there is a clear difference. And in the reference, you can notice high amplitude events. Now, if you are familiar with this type of test and data, you would know that these high amplitude events are associated to fiber failure. And in fact, if you look at the back face of the plate, which is the face forward in the battery pack, so it's the one that you don't want to have any damage on it because it would reduce the clearance that you have with your battery pack, you will see that in the commercial reference, you have a clear puncture with a fiber failure, which suggests very poor structural integrity and poor resistance to a secondary impact, while in the Helicoid you have a very smooth surface, just matrix splits, so just matrix damage, as I showed you earlier, and a much higher structural integrity with no sign of perforation initiation. We also did compare against the real commercial reference, which is the aluminum. And again, the benefits are very high. Once again, we are able to deliver much higher load-bearing capability, but more importantly, in this case, we have a much lower permanent deformation in the plate. compared to the aluminum solution. So overall, the benefit, I would like you to focus on the damage energy and residual clearance. These are percentage improvement over the aluminum solution. You will see that we are able to have 50% less damage in our solution compared to the aluminum, and about 139% larger residual clearance after the impact. Just for you to better understand, this is what residual clearance would look like in the helicoid. It basically goes back flat as it was originally, and this is the aluminum after the impact, where we have about 14 millimeter permanent dent. So you see that the clearance with the battery pack is very much reduced. So we deliver improved safety in this case for both primary but also secondary impact in the structure. We have a roadmap to commercial production. In fact, our special multi-axial design has been validated by multiple suppliers for at volume quotes. As I said, 3,000 tons of material per year. There is a full-scale, fully automated LCM manufacturing cell at TPI that is able to manufacture at scale this component, and we have a full-scale component actually showcased at the Mobility Planet if you want to have a look later on. The next step is to look at how we enable sustainable materials in high-performance applications. As I said, the Helicoid is a fiber architecture, so you can really apply to any fibers, including natural fibers. So we did perform, again, impact tests on full flux solutions, showing that compared to a conventional, we can improve by a great margin performance under impact, in this case, perforation energy. We have an ongoing project with the Department of Energy in the United States to deliver these solutions in a full-scale automotive component with a structural function. And we are also launching with Revel in sporting goods our solution with natural fibers on a pickleball rackets, where we demonstrate an improved sweet spot and therefore improved playability as well as improved durability of the racket. Just to give you a bit more insight on what we can achieve and how we enable sustainability with our solution. If you look at the impact performance of a flux versus glass fiber solution using the same resin, you will see that there is a big gap. It's the full brown dot against the full blue dot. And as soon as we use an hybrid solution where we introduce only 20% of glass fiber in an helicoid version, we reach basically the same performance as the 100% glass fiber solution. So you are able to offset a large amount of material that has a high carbon footprint, such as glass fiber, with one, such as natural fiber, that has a much lower carbon footprint. We are also developing something which is more related to building up hierarchical composite, where we use 100% bio-based additives to the natural fibers that allows us to overcome performance of glass fiber solution. This is a stress versus strain obtained from a flexural test using a PLA as a resin, where we are able to overperform a glass fiber PLA solution, while our solution is 100% bio-based. So again, this is how, through our technology, we enable more sustainable materials in high-performance applications. The last bit I want to talk to you about is also impact fatigue. So far I showed you examples where we have a single impact, but we have done a lot of testing also to demonstrate durability under out-of-plane loading, such as impact fatigue. In this case, it's a collaboration with Mitsui Chemicals, where we use their carbon fiber polypropylene UD tape, Toughnecks, to build a reference cross-ply laminate 090 and compare against an helicoid laminate. Again, using same fiber, same resin, same number of plies, same manufacturing technique. And what we performed is multi-strike impact. So you have your sample, you impacted multiple times in the same spot at the same energy level, and you see how the performance degrades over impact cycles. In this case, the manufacturing was enabled also by airborne through multi-stacking layering that allows to deploy our technology in commercial products. And this is the type of results that you obtain from this test. You will see in black the cross-ply. In this case, we measured the maximum load reached at each impact, over the impact cycles. And you see how quickly they degrade in performance after only 20, 25 impacts. But the helicoid in green, you can see how steady they maintain the high performance over the impact cycles. And only after more than 60 cycles, you see a loss in performance. So we were able to extend more than 90% the durability of this composite, and also have a 42% higher stiffness retention, 15% higher load retention. Again, just changing the layup and having a more optimized layup that parts away from the conventional way of designing composites. These are two images that I hope you can see quite clearly. Otherwise, feel free to come to our booth to have a look at the proper sample, where you can see the damage accumulated in the reference coarse ply after 25 impacts, full perforation, lot of fiber failure, while in our case, after 65 impact cycles, you see very little damage still in the structure. And this brings also to the last point. We started hearing in the last few years about healing of composite structures with a strong focus on the resin, because that's the component that you can heal. The truth is, if you're breaking the fibers, there is no way that you can heal your composite and recover 100% of your performance. So maybe you can achieve only a partial healing. In our case, with our fiber architecture, by dissipating damage through only matrix failure, and delaying, or in some cases avoiding completely the failure of the fiber, like in the samples that I showed you for the glass phenolic reference and the carbon polypropylene sample, you could really achieve a healable composite with a high performance retention. And then it's just a matter of using a resin that you can heal or reprocess, whether it's a thermoplastic, a thermoset with a annealing toughening agent, or new resins like bitumen resins. This is just an example where we perform some tests on an epoxy glass fiber material with the toughening thermoplastic particles at the interface that also act as a healing agent. And this is what happens after impact. You can see this spiraling helicoidal matrix failure in the structure, and this is what you obtain after reprocessing the thermoplastic healing agent, where you get a full recovery of your damage in the structure, as it doesn't have any fiber failure. So in conclusion, what I showed you is, again, the technology has proven performance in several different type of material formats and resin fiber combinations. We enable more sustainable and durable structures in high performance applications. It's a proven scalability, as I showed you with the example on the underbody protection panel of EV battery pack. We have a very versatile value chain integration, because the idea is that we don't want to take business away from anybody, but allow you to make more business by having a unique solutions in your portfolio. Partnerships, of course, are key for us, because that's how we are allowed to do business. We do not create any supply chain disruption. And again, we provide a full product development support through the engineering and the deployment of our technology. And you can use the technology as a platform, meaning that you can cascade from one product to an entire product line, the technology, to deliver performance improvement for different applications. Thank you very much. And if you have any questions, I'm happy to take those. Okay. Yeah. Let's come. Sorry, I just can't hear.
It's working now?
Yeah, maybe. Yeah.
No, the question is, the technology is now still line. I mean, you deploying it, you using it, or you're still in level of prototype testing up to deploy, or what's the status in the market now for your helicoid?
Yeah, so we are launching, our entry market is going to be sporting goods. We are launching with a major ice hockey stick brand. You will have the sticks in the shops in September, so it's already in production. And we are also launching with the pickleball racket. as well. So sporting goods, because it's the lowest hanging fruit, easy entry market for us. As I said, we are doing also works that I haven't shown today on defense applications, where we are a couple of years away from full production, but we have already validated at high TRL our solutions. Aerospace is a very long way ahead, but you see clear applications for these solutions. Containment casing of engine, where we started doing work already. Automotive, our entry market would be, our entry application would be the EV underbody protection panel, which is, the full scale part has been already manufactured. So again, we have proved already high MRL and high TRL. All right. I guess that's all. Thank you very much.